Have you ever wondered why most aircraft in the sky appear gleaming white? It seems like a simple design choice, yet this decision shapes every major airline's fleet worldwide. From Boeing to Airbus, from international carriers to regional airlines, white dominates the commercial aviation landscape. But there's far more to this story than meets the eye. The answer lies in a brilliant combination of physics, economics, and safety considerations that pilots and engineers discovered over decades of aviation history. This choice has become so fundamental to modern air travel that it influences everything from fuel consumption to rescue operations. Understanding why planes are white opens a window into the remarkable science behind every flight we take. The science of solar reflection, the primary reason aircraft are painted white, involves a principle as old as summer itself. White reflects sunlight, while darker colors absorb it, and this fundamental property of light has incredible implications for aircraft flying through the atmosphere. At cruising altitude, where temperatures can drop to -56°C, the airplane's surface still experiences intense solar radiation. Materials like carbon fiber, fiberglass, and plastic composites used in modern aircraft are vulnerable to heat damage and degradation from ultraviolet rays. The white paint acts as a protective shield, minimizing thermal stress and preventing potential structural damage that could compromise safety. Consider the Concorde supersonic airliner, which used special reflective white paint to withstand temperatures generated by flying at twice the speed of sound, reaching speeds of 1,355 miles per hour. This protective function remains crucial for every aircraft today. The economics of color choice. When airlines consider repainting their aircraft, they face unexpected financial challenges that make white the most economical option. A single aircraft repaint costs between $50,000 and $200,000, representing a significant investment for any airline. Beyond the paint itself, applying those new colors adds weight to the aircraft, directly affecting fuel efficiency and operational costs. Research from 2024 shows that paint typically adds between 200 to 400 pounds to an aircraft's weight, depending on size and application. While this may seem minimal, every pound matters in aviation economics. Since fuel represents one of the largest expenses in aviation, this weight difference translates to thousands of dollars in additional costs per year for each aircraft. Interestingly, all commercial aircraft begin their lives painted white at the factory. Airlines choosing distinctive colors must apply extra paint layers on top, incurring these penalties from the moment of delivery. When you consider a major airline operates hundreds of aircraft, the cumulative financial impact becomes staggering and shapes business decisions across the entire industry. Maintenance and safety advantages beyond aesthetics and physics. The white color provides critical practical advantages that improve aircraft maintenance and emergency response. Cracks, dents, oil spills, and other damage become immediately visible against a white background, allowing maintenance crews to identify and repair problems quickly and efficiently. This visibility directly translates to safer, more reliable aircraft for passengers and crew members. In the tragic event of an aircraft incident, rescue teams can locate white aircraft significantly faster than darker alternatives, potentially saving precious minutes during emergency operations. Furthermore, research demonstrates that birds collide with white and light-colored aircraft far less frequently than with darker planes, reducing wildlife strike incidents that can cause serious damage to engines. Each of these factors combined together creates a compelling safety argument for maintaining the white standard in commercial aviation worldwide. Reaching the heavens. Why altitude matters. Commercial aircraft typically cruise at approximately 35,000 feet above sea level, though this can range from 30,000 to 42,000 feet, depending on atmospheric conditions and aircraft type. This specific altitude represents far more than a random choice. It reflects decades of aeronautical engineering and operational optimization. Pilots and airline operators understand that this elevation offers numerous advantages that make it the ideal cruising level for modern air travel. As altitude increases, air becomes progressively thinner, reducing atmospheric resistance and allowing aircraft to burn significantly less fuel while traveling at consistent speeds. However, altitude provides benefits beyond fuel efficiency that enhance the entire flight experience. At these heights, aircraft fly well above weather systems, thunderstorms, and turbulent air pockets that create uncomfortable passenger experiences and place stress on aircraft structures. This combination of fuel economy, passenger comfort, and structural protection has made this cruising altitude the global standard for commercial aviation worldwide. The safety cushion above the Earth. The remarkable altitude commercial flights achieve serves another crucial safety function that many passengers never consider during their journeys. In the unlikely event of an emergency, such as engine failure or hydraulic problems, the height provides pilots with precious time to troubleshoot and implement corrective measures. This altitude functions as a safety buffer, offering crews the opportunity to diagnose problems and execute emergency procedures safely. Additionally, 35,000 feet far exceeds the maximum altitude most bird species can reach. virtually eliminating bird strike incidents that could catastrophically damage an aircraft's engines. While bird strikes are fortunately rare in the upper atmosphere, they remain powerful enough to bring down large aircraft in lower altitudes, as demonstrated in historical incidents. The cruising altitude also ensures sufficient distance from mountainous terrain and other geographical obstacles. These multiple overlapping safety features demonstrate how modern aviation operates as an intricate system where every parameter serves multiple protective functions simultaneously. The mysterious window holes. Passengers often notice small holes in airplane windows and worry about their purpose. Imagining catastrophic scenarios of cabin depressurization and explosive decompression at altitude, the hole, somewhat ominously called the bleed hole, actually serves as an elegant engineering solution to maintaining passenger safety and structural integrity. Understanding this feature requires knowledge of how aircraft cabins maintain the atmospheric pressure necessary for human survival at extreme altitudes. Modern aircraft windows actually consist of 3 separate panes, each serving distinct functions in protecting passengers and maintaining cabin pressure safely. The inner pane is where passengers place their faces and hands during flight, while the middle pane contains the small bleed hole, and the outer pane bears the enormous pressure difference between cabin and atmosphere. The bleed hole equalizes pressure on the middle pane, ensuring that only the outer pane experiences the full stress of pressurization. If the outer pane sustains damage, the middle layer remains intact, protecting passengers from the catastrophic effects of cabin pressure loss. Flying the world's routes. Understanding ETOPS regulations. Despite advanced technology and incredible aircraft capabilities, commercial aviation maintains strict regulations limiting where planes can fly based on engine requirements and safety standards. The key to understanding polar flights lies in a regulation called ETOPS, Extended Range Twin Engine Operations Performance Standards. These regulations ensure that aircraft can safely reach a diversion airport if an engine fails. Determining which routes are accessible and which remain off. Twin-engine aircraft typically must stay within 120 minutes of an available airport, a requirement that makes most polar regions impractical for commercial operations. However, aircraft with 3 or 4 engines have extended capabilities, allowing them to fly transpolar routes more readily. Additionally, flying near Earth's magnetic poles wreaks havoc on navigational equipment, disorienting pilots and making accurate flight path maintenance extremely difficult. The harsh environmental conditions and limited airport infrastructure mean that any survivors of an incident would face nearly impossible circumstances. These factors combine to create a compelling operational and safety argument for most commercial routes, keeping aircraft and passengers safe by respecting geography and technology limitations. Join us at the World Documentaries to explore more fascinating aviation mysteries and share your own experiences and questions in the comments below.